Hello there and welcome back to the Science Sleepy Minds. You're lying somewhere soft right now. Perhaps a bed that has learned the shape of your body. Perhaps a couch that has seen better days but still holds you like an old friend. Above you, there is a ceiling, and beyond that ceiling, there is a roof. And beyond that roof, there is sky. And beyond that sky, well, that is exactly what we're here to talk about tonight. You are about to tumble down one of the strangest rabbit holes in all of cosmology, a question so deliciously contradictory that it has kept philosophers awake for millennia and physicists arguing at conferences where the coffee is always slightly too cold. Can the universe be infinite and still have an edge? Let that sink in for a moment. Something that goes on forever, stretching in every direction without end, and yet somehow, impossibly, also having a boundary, a limit, a place where the everything becomes the nothing. You probably will not survive this question with your intuition intact, but that is perfectly fine. Your intuition was built for finding ripe fruit and avoiding large predators, not for wrapping itself around the architecture of existence itself. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop a comment telling me where you're listening from tonight and what time it is in your corner of the world. I love imagining this little community scattered across the globe, some of you watching the sun rise while others watch it set, all of us united by this strange hunger to understand what lies at the edge of everything. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You take a breath and you let yourself drift into the question, the universe. That word gets thrown around so casually, does it not? You hear it in movies, in science documentaries, in the dramatic voiceovers of nature programs. But what does it actually mean? At its most basic, the universe is simply everything that exists. Every atom, every photon, every wisp of dark matter lurking invisibly between the galaxies, every thought you have ever had, every dream you will ever dream, every grain of sand on every beach on every planet orbiting every star in every galaxy, spinning through the void. All of it, the totality, the whole cosmic enchilada, as some astronomers have affectionately called it, though historians still argue whether that phrase originated in a serious lecture or after one too many drinks at an observatory. Now, when you ask whether this everything can be infinite, you're really asking whether there is a limit to existence itself, and when you ask whether it can have an edge, you're asking whether that limitless existence somehow ends. Already you can feel your brain beginning to protest. These two ideas seem to be opposites. Infinity means no end. An edge means an end. How can something have no end and also have an end? It sounds like asking whether a circle can have corners, or whether silence can be loud, or whether your cat can love you and also knock your water glass off the table on purpose. Actually, that last one is definitely possible. Cats contain multitudes. But here is where the paradox starts to unfold into something more interesting. The word edge can mean different things depending on what you're talking about. Think about the surface of the Earth for a moment. You're standing on it right now, or lying on it, or hovering slightly above it on a mattress that is, in turn, resting on a floor that is attached to a building, that is anchored to the ground, that is part of the crust that wraps around the planet. The surface of the Earth is finite. It has a specific area, about 510 million square kilometers, if you want to get technical about it. And yet, if you started walking in one direction and just kept going, you would never reach an edge. You would never fall off. You would simply walk and walk and walk until eventually, after a very long time and a lot of sore feet, you would end up right back where you started. The surface is finite but unbounded. It has no edge, yet it does not go on forever. This is the kind of mental stretching exercise you need to warm up with before tackling the universe itself. Because the universe might be playing a similar trick, just in more dimensions than you can easily visualize. Imagine for a moment that you're a tiny two-dimensional creature living on the surface of a balloon. You can move forward and backward, left and right, but you have no concept of up or down. To you, your world is flat, stretching out in all directions. If someone asked you whether your universe had an edge, you would say no, of course not. You could travel forever and never hit a wall. But if someone asked you whether your universe was infinite, you would also say no, because if you measured carefully, you would find that your world curved back on itself. It had a finite area. It was a closed surface. Now, here is the quirky part. In 1865, a mathematician named August Mobius played around with a strip of paper and created the famous Mobius strip, a surface with only one side and one edge. It is the kind of object that makes you question what edges even mean. If a simple strip of paper can be twisted into something so counterintuitive, imagine what the fabric of spacetime might be capable of. The question you're settling into tonight is not a new one. Humans have been staring up at the night sky and wondering about its limits for as long as there have been humans to stare and skies to wonder at. The ancient Babylonians mapped the stars and imagined a great dome overhead. The ancient Egyptians saw the sky goddess Nut arching her body across the heavens. Every culture has had its own version of the cosmic architecture, its own answer to the question of what lies beyond. And every answer has eventually given way to a newer, stranger, more wonderful answer. You are part of that tradition now. You're lying in the dark, breathing slowly, letting your mind reach outward toward the edges of everything. Or the lack of edges. Or the edges that are not really edges, but something else entirely. Something that does not have a name yet, because human language was not built for this kind of geography. The universe might be infinite. It might stretch on forever, galaxy after galaxy, void after void without end. Or it might be finite, wrapping back on itself in some higher dimensional origami that your three-dimensional brain cannot quite picture. Or it might be something else, something that does not fit neatly into either category, something that laughs at the very question and invites you to think harder. And the edge? Well, that depends on what you mean by edge. There might be a horizon, a limit to what you can see, beyond which light has not had time to reach you. There might be a boundary, a place where the universe meets something else, or nothing else. There might be no edge at all, just more and more universe forever and ever. Amen. Tonight, you're going to explore all of these possibilities. You're going to travel back in time to meet the first humans who asked this question, and you're going to travel forward to meet the physicists who are still wrestling with it today. You're going to bend your mind around shapes that do not exist in everyday experience and concepts that sound like they belong in a fever dream. And through it all, you're going to breathe slowly. Let your body relax and trust that the universe will still be there in the morning, edges or no edges, infinite or finite, mysterious and beautiful and utterly unconcerned with whether you understand it or not. So let yourself sink a little deeper into wherever you're resting. The journey is just beginning, and you have nowhere else to be. You drift backward now, not through space but through time, settling into an era when the sky was closer, or at least felt that way. Imagine yourself as one of the first humans to lie on your back and really look up. Not a quick glance to check for predatory birds or storm clouds, but a genuine, prolonged stare into the darkness above. You're somewhere in Africa, perhaps, or the Middle East, or the grasslands of Asia. The exact location does not matter as much as the experience. There are no city lights, no airplanes, no satellites blinking their way across the dome. Just you and the stars, thousands upon thousands of them, scattered like spilled salt across an infinite black tablecloth. Actually, that is the question, is it not? Infinite? Or just very, very large? The earlier sky-gazers did not have the vocabulary you do. They did not know about galaxies or light years or the expansion of space-time. But they had eyes, and they had wonder, and they had the deeply human compulsion to make sense of what they saw. And what they saw was a ceiling, or a bowl, or a tent. The metaphors varied from culture to culture, but the underlying intuition was similar. The sky was something, not nothing. It had a shape. It had a limit. Somewhere up there the stars stopped, and something else began. The ancient Mesopotamians, those clever people who gave us writing and mathematics and the 60-minute hour, imagined the sky as a solid dome made of some kind of celestial metal. The stars were holes in this dome, or perhaps lights attached to it, revolving around the earth in stately circles. Beyond the dome was water, a primordial ocean that had existed before creation and still lurked on the other side, held back by the firmament. This was not a universe without edges. This was a universe that was mostly edges. A cozy cosmic room with walls and a ceiling and a floor, everything in its proper place. Historians still argue whether the Mesopotamians truly believed in this literal dome, or whether it was a poetic metaphor that later generations interpreted too literally. The distinction between myth and science was not as sharp back then as we like to pretend it is now. People could hold multiple truths simultaneously, understanding that the sky was both a goddess and a physical barrier, both a story and a structure. Meanwhile, over in ancient Egypt, the sky had a name and a body. She was Nut, the goddess who arched herself over the earth each night, her star-spangled form stretching from horizon to horizon. Her brother Geb was the earth below, and their father Shu, the god of air, held them apart so that creation could exist in the space between. The edge of the universe in this telling was wherever Nut's fingers and toes touched the ground. Beyond that was the realm of the gods, the Duat, a place of mystery and transformation where the sun went to die and be reborn each day. You might be tempted to smile at these ancient cosmologies, to pat them on the head and congratulate them for trying their best with limited information. But consider this. They were asking the exact same question you're asking tonight. What is out there? Does it end? What happens at the edge? The fact that their answers involved goddesses and metal domes does not make the questions any less profound. If anything, it shows how deeply the human mind needs to grapple with boundaries. You cannot simply look at infinity and accept it. Your brain demands a frame, a container, a place where the picture ends and the wall begins. This is a quirky psychological fact that scientists have studied extensively. Human beings are terrible at intuiting infinity. Show someone a line and ask them to imagine it going on forever, and they will nod and say they understand, but their mental image will almost always include some kind of endpoint, even if it is fuzzy and far away. We are creatures of edges. We evolved in a world of horizons and coastlines and mountain ranges, places where one thing ends and another begins. Asking us to genuinely comprehend a universe without edges is like asking a fish to comprehend the desert. We can use the words, but the concept slips through our mental fingers. The ancient Chinese had their own cosmological models, some of which were remarkably sophisticated. The Xuanye school, for instance, proposed that the heavens were empty and infinite, with celestial bodies floating freely through a void that had no boundaries. This was a radical idea for its time, and it coexisted with other models that imagined the sky as a hemisphere covering a square Earth, or a series of nested spheres carrying the planets and stars. Scholars still argue whether the Xuanye conception of infinity was truly infinite in the modern sense, or simply very, very large, which is a distinction that matters more than you might think. The Greeks, as they did with so many things, took the question and turned it into a full-contact philosophical sport. You will meet them properly in just a moment, but for now, notice how the pattern repeats. Every culture that looked up at the sky eventually asked the same questions. Is there a wall out there? a fence, a curtain, or does the darkness just go on, indifferent to human categories? And here is the thing that might keep you awake if you let it. We still do not know. 4,000 years of staring, 2,000 years of philosophy, 400 years of modern science, and the question remains open. The universe might be infinite. It might not be. There might be an edge out there, impossibly far away, or there might be no edge at all, just more space, more galaxies, more questions. The ancient Egyptians and Mesopotamians were guessing, but so are we. Our guesses are better informed, backed by mathematics and telescopes and satellite data, but they are still guesses. The cosmic architecture remains hidden behind the limits of what we can observe, teasing us with clues but never quite revealing the full blueprint. You feel yourself relaxing a little deeper as you consider this. There is something comforting about joining such a long tradition of wondering. You're not alone in your curiosity. You're part of a lineage that stretches back to the first campfires, the first stories, the first humans who lay on their backs and asked the darkness what it was hiding. The answers have changed, but the question has not, and maybe that is okay. Maybe the question is the point, a kind of eternal flame that each generation tends and passes on, never quite extinguishing, never quite illuminating everything. The stars above those ancient sky gazers were the same stars you can see tonight, if you are lucky enough to live somewhere dark. Well, almost the same. Stars are born and die over millions of years, and the constellations slowly shift as the sun moves through the galaxy. But the Milky Way still stretches overhead, a river of light that every human culture has noticed and named. The Babylonians called it the Serpent of the Night. The Greeks called it the Milk of Hera, spilled across the sky when Hercules nursed too vigorously. The Cherokee called it the path where a dog scattered stolen cornmeal as it ran from angry villagers. Every story is an attempt to put an edge around the incomprehensible, to make the infinite feel a little more like home. You're breathing slowly now, in and out, letting the ancient sky settle over you like a blanket made of questions. The edge of the universe is still out there, or not out there, waiting to be found or proven non-existent. But for now, it is enough to know that you are looking, that you've always been looking, that looking is what humans do when the night is clear and the world is quiet and the stars are too beautiful to ignore. You find yourself now in ancient Greece, and the air smells of olive oil, sea salt, and vigorous disagreement. The Greeks did not invent philosophy, but they certainly perfected the art of arguing about everything, and the nature of infinity was one of their favourite topics. You settle into a marble colonnade somewhere, perhaps in Athens, perhaps in one of the coastal cities where thinkers gathered to debate the fundamental structure of reality. The sun is warm, the wine is watered, and someone is about to say something that will echo through the next 2,000 years. Let us start with Aristotle, because everyone starts with Aristotle. He was the kind of thinker who had an opinion about everything: biology, politics, ethics, the proper way to write a tragedy, and his opinion about infinity was clear and emphatic. It does not exist. Or rather, it exists only as a potential, never as an actual thing. You can always add one more number, take one more step, divide a line one more time, but you will never arrive at infinity itself. It is a horizon that recedes as you approach, always there in theory, never there in practice. This might sound like a minor philosophical quibble, but it had enormous implications for the question of the universe's edge. If actual infinity is impossible, then the universe must be finite. It must have a boundary somewhere, a place where space gives way to not space. Aristotle imagined the cosmos as a series of nested crystalline spheres, with the Earth at the centre and the stars fixed to the outermost sphere. beyond that outermost sphere? Nothing. Not even empty space, because empty space would still be something, and there could not be anything beyond the edge of everything. You might be wondering what happens if you reach that outermost sphere and try to stick your hand through. The Aristotelian answer is that the question does not make sense. There is no through to stick your hand. The edge of the universe is not like the edge of a table, where you can fall off into the space beyond. It is more like the edge of a painting, where the canvas simply ends and there is no beyond to speak of. Except, of course, you can walk around a painting and see its back, which rather undermines the metaphor. Philosophy is hard. Not everyone agreed with Aristotle, though. A generation earlier, a thinker named Archytas of Tarentum had posed one of the most famous thought experiments in the history of cosmology. Imagine, Archytas said, that you travel to the edge of the universe. You're standing at the very boundary, the place where everything ends. Now reach out your hand, or throw a spear, or shoot an arrow. What happens? If your hand passes through, then the boundary was not really the edge. There was more space beyond, and you have not reached the true limit. But if your hand cannot pass through, something must be blocking it, and that something exists beyond the supposed edge, which means the edge was not really the edge either. The argument is delightfully simple and maddeningly difficult to refute. Either way, Archytas argued, the edge retreats. Either way, there is more, and if the edge always retreats, then there is no edge, and the universe must be infinite. Historians still argue whether Archytas himself believed the universe was truly infinite, or whether he was simply making a logical point about the incoherence of edges. The ancient sources are fragmentary, and philosophers love to attribute clever arguments to earlier thinkers who may or may not have actually made them. But the spear argument, as it came to be known, lodged itself in the Western philosophical tradition like an arrowhead in a wound, irritating every subsequent thinker who tried to imagine a finite cosmos. And then there were the atomists, those wonderful contrarians who believed that everything was made of tiny indivisible particles moving through an infinite void. Democritus and his followers imagined a universe with no edges at all, just an endless expanse of emptiness, punctuated by countless worlds, some like ours and some utterly different. There might be a world out there where you made different choices, married a different person, took a different job. There might be a world where elephants fly and fish recite poetry. In an infinite universe, everything that can happen does happen. Somewhere, somewhen. This is a quirky fact that many people do not realise. The idea of the multiverse is not a modern invention. The atomists were proposing something remarkably similar 2,400 years ago, and they did it without telescopes, without mathematics, without any of the tools we consider essential to cosmology. They did it through pure reasoning, sitting in the shade and thinking very hard about what existence must be like. The Stoics, by contrast, returned to a finite cosmos, but with a twist. They imagined the universe as a living organism, a vast cosmic animal breathing in and out over unimaginably long cycles. During the expansion phase, the universe spread out and differentiated into the complexity we see around us. During the contraction phase, everything collapsed back into a primordial fire, a great conflagration that destroyed all distinctions and prepared for the next cycle. This universe had an edge, the edge of the cosmic organism, but it also had infinite time, cycling through its expansions and contractions forever. You're starting to notice a pattern now, are you not? Every attempt to grapple with infinity and edges leads to new questions, new paradoxes, new thought experiments that reveal the limitations of the previous answers. The Greeks were not stupid. They were actually extraordinarily clever, which is why their ideas kept generating problems that required even more cleverness to address. One of the most elegant formulations came from the philosopher Lucretius, writing in Latin but drawing on Greek atomist ideas. In his epic poem On the Nature of Things, Lucretius asked his readers to imagine standing at the supposed edge of the universe and throwing a javelin. His conclusion was the same as Archytas's: the edge must always retreat, because there must always be space for the javelin to fly through. But Lucretius went further, using this argument to support a thoroughgoing materialism that denied the gods any role in creating or maintaining the cosmos. The universe was infinite, eternal, self-sufficient, and utterly indifferent to human prayers. Quite the bedtime reading, actually. The legacy of these debates is still with us. When modern physicists talk about whether the universe is finite or infinite, bounded or unbounded, they are replaying arguments that first crystallized in the Mediterranean sunlight 2.5 millennia ago. The vocabulary has changed, the mathematics has become vastly more sophisticated, but the basic conceptual moves, imagining yourself at the edge, asking what happens when you reach out, remain surprisingly similar. You breathe in the imaginary olive-scented air and let the Greek philosophers fade back into history. Their questions were good questions. Their answers were incomplete, but all answers are incomplete when you are dealing with infinity. The edge of the universe is still out there, somewhere or nowhere, waiting for someone to throw another spear and see where it lands. The stars are coming out now in your mental sky, the same stars the Greeks saw, and you feel yourself connected to that long tradition of wondering. You're not the first to ask these questions, and you will not be the last. The conversation continues, across the centuries, across the edges that may or may not exist. The scene shifts, and you find yourself in a world lit by candles and oil lamps, a world where the great libraries hold handwritten manuscripts, and the smartest people alive are trying to reconcile ancient philosophy with the demands of faith. You're in the medieval period now, somewhere between the fall of Rome and the rise of modern science, a span of roughly 1,000 years during which European and Islamic scholars wrestled with the same questions the Greeks had posed, but with new urgency and new constraints. The constraint, of course, was God, or Allah, or the divine in whatever form a particular culture understood it. If the universe was infinite, what did that mean for the Creator? If space stretched on forever, was there room for heaven? If time had no beginning, was there a moment of creation? These were not abstract puzzles for medieval thinkers. They were matters of salvation and damnation, questions that could get you celebrated as a saint or burned as a heretic, depending on how you answered and who was listening. Let us start with the Islamic scholars, because they got to the Greek texts first. While Western Europe was busy with feudalism and forgetting how to read, the Islamic world was translating Aristotle, Plato, and the atomists into Arabic, and arguing about them with tremendous sophistication. Scholars like Al-Kindi, Al-Farabi, and Ibn Sina, known in the West as Avicenna, developed elaborate cosmologies that tried to harmonize Greek philosophy with Islamic theology. The universe, in their telling, was finite but surrounded by the light of God, a divine radiance that transcended space and time and made infinity unnecessary. But not everyone agreed. A thinker named Ibn Rushd, Averroes to the Latins, argued that the universe was eternal, having existed forever alongside God rather than being created at a specific moment. This was a controversial position, to say the least. It suggested that creation was not a singular act of divine will, but an ongoing process, the universe eternally flowing from God's nature like light, eternally flowing from a flame. Historians still argue whether Ibn Rushd truly believed this or was simply presenting it as a philosophical possibility, one interpretation among many. The question of infinity took on special significance in Islamic thought because of the nature of God. Allah is described in the Quran as infinite in power, knowledge, and mercy. If God is infinite, can creation also be infinite? Or would that somehow diminish divine uniqueness? The theologians split into camps. Some argued that only God could be truly infinite, so the universe must be finite by definition. Others argued that an infinite God might choose to create an infinite universe as an expression of that very infinitude. The debate never fully resolved, which is perhaps appropriate for a question about infinity. Meanwhile, in Christian Europe, the rediscovery of Aristotle sparked a philosophical revolution. When the Arabic translations made their way westward, along with the commentaries of Islamic scholars, European thinkers suddenly had access to a complete philosophical system that explained everything from physics to politics. The problem was that Aristotle's system did not quite fit Christian doctrine. Aristotle believed the universe was eternal, which contradicted the Genesis account of creation. Aristotle believed the soul was the form of the body, which made resurrection awkward to explain. And Aristotle believed actual infinity was impossible, which raised questions about the nature of God's power. Could God create an infinite universe if God wanted to? This question obsessed 13th century scholastics like Thomas Aquinas, who tried to navigate between respecting Aristotle's logic and maintaining God's omnipotence. Aquinas concluded that while God could create anything that was logically possible, and while an actually infinite universe might not be logically contradictory, God had in fact chosen to create a finite universe with a definite beginning. The universe had an edge, and that edge was the boundary between creation and creator. Here is a quirky fact that might amuse you. In 1277, the Bishop of Paris issued a list of 219 propositions that scholars were forbidden to teach on pain of excommunication. Many of these condemned propositions were Aristotelian ideas that had become too popular among university intellectuals. One of the forbidden claims was that God could not create more than one world. The bishop insisted that God's power was unlimited and could create infinite worlds if it pleased him to do so. This condemnation, ironically, may have helped open the door to modern cosmology by encouraging thinkers to imagine possibilities beyond the Aristotelian framework. The medieval imagination was haunted by the edge of the universe. Maps from this period often showed the known world surrounded by ocean, and the ocean surrounded by darkness, and the darkness surrounded by the realm of God. The cosmos was a nested hierarchy of spheres, with the Earth at the centre, the planets in their orbits, the stars fixed to the outermost sphere, and beyond that sphere, what? The Empyrean, some called it. The heaven of light and fire where God and the angels dwelt. This was not physical space, but spiritual space, a realm beyond measurement and location. But even this scheme generated paradoxes. If God was everywhere, was God inside the universe or outside it? If heaven was beyond the stars, was it infinitely far away or somehow present in a dimension perpendicular to ordinary space? The mystics, those troublemakers who sought direct experience of the divine, reported encounters with infinity that defied all categories. Meister Eckhart, the German mystic, spoke of the soul dissolving into the groundless ground of God, a formless infinite that contained all things without being any particular thing. The inquisitors were not amused. You feel yourself sinking into this strange medieval world where every question about the universe was also a question about God, and every answer had to satisfy both reason and revelation. It was not easy. Scholars wrote enormous commentaries, arguing over single sentences for decades, trying to find formulations that preserved both philosophical coherence and theological orthodoxy. Many failed, some were condemned, a few were later declared saints, and through it all, the edge of the universe remained tantalizingly unclear. Was it a physical boundary or a spiritual one? Was it infinitely far away or somehow folded into a higher dimension? Could you reach it by travelling outward, or only by turning inward, seeking the infinite at the centre of your own soul? These questions might seem quaint now, relics of a pre-scientific age, but they were not stupid questions. They were attempts to take infinity seriously, to follow the logic wherever it led, even when it led to uncomfortable places. The medieval thinkers knew that infinity was dangerous, that it threatened to swallow all categories and distinctions, that it made the human mind feel very small and the universe feel very strange. They were right to be cautious. Infinity is dangerous. It is also beautiful, in the way that all dangerous things are beautiful when viewed from a safe distance. You breathe slowly, letting the candlelit world fade, letting the medieval scholars return to their manuscripts. Their questions are still with us, translated into the language of physics and cosmology. Is the universe infinite? Does it have an edge? What lies beyond? The faith has changed for many people, but the wonder remains. You emerge from the medieval period into a world of powdered wigs, falling apples, and the slow explosion of modern science. The year is 1687, give or take, and a man named Isaac Newton has just published a book that will change everything. The Principia Mathematica lays out the laws of motion and gravity in precise mathematical form, explaining why planets orbit the sun, why apples fall from trees, why the tides rise and fall. It is one of the most influential books ever written, and it has some very strange things to say about the edge of the universe. Newton needed space, not personal space. He was famously cranky and did not much care for other people, but physical space, a vast stage on which his cosmic drama could unfold. His laws of gravity worked by describing how every massive object attracted every other massive object, with a force proportional to their masses and inversely proportional to the square of the distance between them. Simple enough in principle. But if you start doing the math, you run into problems. Imagine a finite universe, a bubble of matter floating in empty space. Every star and planet in this universe is pulling on every other star and planet. The objects near the centre feel roughly equal pulls from all directions, so they stay put. But the objects near the edge feel a net pull toward the centre, because there is more matter on one side of them than the other. Over time, this pull would cause the entire universe to collapse inward, all the stars and planets rushing toward the centre in a cosmic traffic accident of unimaginable proportions. Newton saw this problem clearly. A finite universe left to itself would collapse under its own gravity. The stars would not hang motionless in the heavens, they would fall. But the stars did seem to hang motionless, at least as far as 17th century telescopes could tell. So something must be preventing the collapse. Newton's solution was elegant in its simplicity. Make the universe infinite. In an infinite universe, there is no centre and no edge. Every point is surrounded by an equal amount of matter in all directions, stretching out to infinity. The gravitational pulls balance perfectly, and nothing collapses. The stars can float in their fixed positions forever, each one held in place by the infinite web of attractions from all the other stars. Problem solved. Except, of course, it was not solved at all. Newton had traded one problem for another, and the new problem was arguably worse. An infinite universe filled with an infinite number of stars should be infinitely bright. Every line of sight in every direction should eventually terminate on the surface of a star. The night sky should not be dark. It should be a blinding wall of light, as bright as the surface of the sun, in every direction, forever. This is clearly not what you see when you look up at night. The sky is dark. There are stars, yes, but there are also vast stretches of blackness between them. Where did all the light go? Newton himself never fully grappled with this paradox. He noted it, worried about it, and moved on to other things like inventing calculus and arguing with Leibniz. But the problem lingered, a loose thread in the Newtonian tapestry that would not be properly pulled until centuries later. Here is a quirky historical fact. Newton believed that space itself was the sensorium of God, a kind of divine nervous system through which God perceived and sustained creation. Infinite space was not just a mathematical convenience, it was a theological necessity, the medium through which an infinite God could be present at every point in the universe simultaneously. This idea made some of Newton's contemporaries uncomfortable. If space was God's sensorium and space was infinite, did that mean God had an infinite body? The theological implications were dizzying. Historians still argue about how seriously Newton took his own metaphysical speculations. He was a deeply religious man, spending as much time studying biblical prophecy and alchemy as he did studying physics. But he was also careful about what he published, knowing that some ideas were too controversial for public consumption. His private writings reveal a mind constantly wrestling with the implications of his own discoveries, trying to fit them into a coherent worldview that included both rigorous mathematics and fervent faith. The infinite universe that Newton required was a strange place. It was absolute, existing independently of the matter it contained. It was uniform, the same everywhere, with no special locations or directions. It was eternal, having existed forever in the past and stretching forever into the future. And it was relational to nothing. There was no outside to Newton's infinite space, no edge where space ended and something else began. Space simply was, the stage on which all cosmic events unfolded, unchanging and unchangeable. This Newtonian space became the default assumption of physics for the next 2 centuries. Scientists worked within it, measuring and calculating, assuming that the universe was a vast infinite container filled with matter and governed by simple mathematical laws. The edge of the universe in this framework did not exist. There was no edge. There was only more space, more stars, more emptiness stretching out forever. But the problems did not go away. They just got pushed into the background, waiting for someone to notice them again. The gravitational collapse problem, which Newton had tried to solve with infinity, turned out to be unstable. Even a tiny perturbation in an infinite universe would cause local regions to collapse, forming clumps and clusters that would eventually become the galaxies and galaxy clusters we see today. Newton's infinite universe was not a static equilibrium. It was a precarious balance, ready to tip at the slightest nudge. And the darkness of the night sky remained unexplained, a nagging puzzle that suggested something was wrong with the picture. Either the universe was not infinite, or it was not filled with an infinite number of stars, or there was some mechanism absorbing or blocking the light, or something else entirely was going on. Newton did not know, and neither did his successors for another 150 years. You settle into this Newtonian universe, feeling its vastness stretching out around you. It is a cold and lonely place, in some ways, an infinite stage where matter dances according to mathematical laws, with no edge, no boundary, no limit. But it is also a magnificent place, a universe where the human mind can reach out with equations and understand, at least partially, how the cosmic clockwork operates. The stars above you are obeying Newton's laws right now, pulling on each other across the light years, maintaining their delicate dance. And somewhere out there, infinitely far away, there are more stars, and beyond those more still, forever and ever. Or so Newton believed. The truth, as you will discover, is both simpler and stranger. The night sky is dark. You've probably never thought of this as a paradox, but now you cannot unthink it. If the universe is infinite and filled with an infinite number of stars, why is the sky not blazing with light? Why are there dark patches between the stars? Why can you see anything at all except an endless, uniform glare? This puzzle has a name, Olbers' paradox, after the German astronomer Heinrich Wilhelm Olbers, who popularized it in 1823. But the problem had been noticed much earlier. Kepler mentioned it. Halley worried about it. Even Newton was aware that his infinite universe had this awkward feature. The question had been hanging in the air for centuries, waiting for someone to give it a catchy name and a rigorous formulation. Here is the argument, stripped to its essentials. Imagine you're standing in an infinite forest. The trees are scattered randomly, some near, some far, but there are infinitely many of them, stretching out in every direction. Now imagine you look along any line of sight. Eventually that line must hit a tree. It might be a nearby tree or a very distant tree, but in an infinite forest with an infinite number of trees, every sight line terminates at some trunk. You should not be able to see anything except trees. The entire horizon should be wall-to-wall bark. Now replace trees with stars. In an infinite universe with an infinite number of stars, every line of sight should eventually hit a stellar surface. The night sky should be uniformly bright, every point filled with the light of some distant star. The fact that it is not, that you can see dark gaps, that the night is mostly black with scattered points of light, means something is wrong with our assumptions. Olbers himself proposed a solution. Maybe there is dust and gas between the stars, absorbing the light from distant sources. This would explain the darkness. But the solution does not actually work, as later scientists realized. If the dust absorbed starlight, it would heat up. Eventually the dust would reach the same temperature as the stars and start glowing itself. You would just have replaced a wall of stellar light with a wall of dust light. The sky would still be blindingly bright. Historians still argue about how much Olbers understood his own paradox. His original paper focused on the dust hypothesis and did not fully explore its limitations. Later generations refined the argument, making it sharper and more troubling. By the late 19th century, Olbers's paradox was a recognized puzzle in cosmology, a loose end that nagged at anyone who thought seriously about the structure of the universe. Here is a quirky fact that might amuse you. Some people tried to solve the paradox by proposing that distant starlight was tired. Maybe light lost energy as it travelled, slowly fading over vast distances until it became too dim to see. This tired light hypothesis was taken seriously for a while, but it turned out to have its own problems. Tired light would spread out in wavelength, blurring the images of distant galaxies in ways that we do not observe. The hypothesis eventually faded away, much like the light it was trying to explain. The resolution to Olbers' paradox came from an unexpected direction. Time. The universe is not infinitely old. It had a beginning, or at least the matter and energy we can see had a beginning, about 13.8 billion years ago. This means that light from the most distant stars has only been travelling for a finite time. There are stars so far away that their light has not had time to reach us yet. The universe might be infinite in extent, but it is finite in age, and that finitude creates a horizon beyond which we cannot see. You can think of it like standing in that infinite forest, but the forest only came into existence a few hours ago. The trees are all there, infinitely many of them, but the light from the most distant trees has not had time to reach your eyes. You see nearby trees clearly, slightly more distant trees more faintly, and beyond a certain point only darkness. Not because there are no trees, but because the light is still on its way. This solution ties Olbers's paradox to the deeper question of the universe's history. The darkness of the night sky is evidence that the universe had a beginning. Every time you look up at the stars and see the black gaps between them, you're seeing proof that creation is not eternal, that there was a moment, or something like a moment, when everything started. But wait. You might be wondering whether this resolution proves that the universe is finite after all. If light from distant stars has not reached us, does that mean those stars are beyond some kind of edge? Not exactly. The horizon created by the finite age of the universe is not a physical boundary. It is a limitation of observation, not of existence. Beyond the horizon, space might continue indefinitely, filled with stars and galaxies we will never see because their light will never reach us. The edge, in this sense, is personal. It is your edge, the limit of your cosmic vision, not the limit of the cosmos itself. This distinction will become important later when we talk about the observable universe and what lies beyond it. For now, just notice how the resolution of Olber's paradox shifts the question. We're no longer asking whether the universe has an edge in space. We're asking whether it has an edge in time. And the answer to that question turns out to be yes, sort of, but also no, kind of, depending on what you mean by edge and time. Cosmology is fun that way. You let the darkness of the night sky settle over you, appreciating it in a new way. That darkness is not an absence. It is a message, written in the language of light and time, telling you that the universe has a history. The stars were not always there. The galaxies were not always there. Once there was something else, a hot, dense state of pure energy that eventually expanded and cooled and condensed into the structures we see today. The edge of that beginning is still visible in a sense if you know how to look. The night is quiet now, and the stars are patient. They have been shining for billions of years, and they will keep shining for billions more, waiting for someone to ask the right questions. You are asking them right now in the dark, and the universe is answering in the only way it knows how, with light, and with the darkness between the light, and with the mystery that lies beyond both. The year is 1915, and a man with wild hair and a violin is about to break the universe. Not literally, of course. Albert Einstein was gentle with most things except other physicists' egos, but conceptually, dramatically, permanently. His general theory of relativity is about to show that space and time are not the fixed stage Newton imagined, but a dynamic, flexible fabric that bends and warps and stretches in response to the matter and energy it contains. And once you realize that space-time can bend, the question of the universe's edge becomes something entirely different. You settle into this early 20th century feeling the intellectual excitement crackling in the air. Quantum mechanics is emerging from its cocoon. Atomic physics is revealing the structure of matter, and Einstein, having already revolutionized physics once with special relativity, is about to do it again. The core insight of general relativity is deceptively simple. Gravity is not a force, or rather, it is not a force in the way Newton imagined, a mysterious action at a distance that reaches across empty space to pull objects together. Instead, gravity is the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space and time around them, and other objects follow curved paths through this warped geometry. The Earth does not pull the apple down. The Earth curves the space around it, and the apple follows the most natural path through that curved space, which happens to lead toward the ground. This might sound like semantic juggling, but the implications are profound. If space-time can curve, it can curve in all sorts of ways. It can curve gently, like the surface of a very large balloon. It can curve sharply, like the region around a black hole. And crucially, it can curve back on itself, creating geometries that have no edge even though they are finite. Remember the surface of the Earth? Finite but unbounded, limited in area but edgeless. You can walk forever without reaching a boundary. General relativity allows the same kind of geometry for the universe as a whole, but in 3 dimensions instead of 2. Imagine a universe that curves back on itself, where travelling far enough in any direction eventually brings you back to where you started. This universe would have a finite volume. You could, in principle, measure how much stuff it contained, but no edge. There would be no wall, no boundary, no place where space ends and something else begins. This is called a closed universe, and it was one of the first cosmological models Einstein explored. In a closed universe, the total amount of matter and energy determines the curvature. Enough matter, and the universe curves positively, wrapping around itself like a hypersphere. Not enough matter, and the universe curves negatively, shaped like an infinite saddle that stretches out forever. Just the right amount, and the universe is flat, Euclidean, extending without curve to infinity. Historians still argue about Einstein's initial motivations for exploring cosmology. His famous cosmological constant, a fudge factor he added to his equations to allow for a static universe, was later called his greatest blunder, though some physicists today think it might have been a blunder in the right direction. Einstein wanted a universe that did not change, that sat in eternal equilibrium, neither expanding nor contracting. The cosmological constant was his way of propping up this static vision against the natural tendency of gravity to pull everything together. Here is a quirky fact. Einstein originally envisioned a finite closed universe that was roughly spherical, with space curving uniformly in all directions. If you could somehow see far enough, you would eventually see the back of your own head, light having travelled all the way around the cosmos. This was not a metaphor, but a literal prediction of the geometry. In a sufficiently curved, closed universe, parallel lines eventually meet, straight paths eventually return to their starting point, and looking outward is eventually the same as looking inward. The mathematics of general relativity are notoriously difficult. Einstein himself needed help from his friend Marcel Grossmann, a mathematician, to work out the details, but the conceptual picture is almost poetic. The universe is not a box, it is not a stage. It is a living geometry shaped by its contents, evolving over time, capable of configurations that Newton never imagined. But here is the crucial point for our question. Even in an infinite universe, general relativity allows for strange boundaries. The curvature does not have to be uniform. Space can be flat overall, but have regions of intense curvature, like wells and hills in an otherwise level landscape. And the overall topology, the way space connects to itself, can be more complicated than simple sphere or saddle. You could have a flat universe that wraps around in some directions but not others, like a cosmic video game screen where going off the left edge brings you back on the right, but up and down go on forever. These topological possibilities are still debated by cosmologists today. The universe might be infinite, or it might be finite but unbounded, or it might be something more exotic that we have not quite figured out yet. General relativity allows all these options. The equations do not pick one. To know which geometry we live in, we have to look at the actual universe, measure its curvature, study its large-scale structure, and try to infer its shape from the data. You feel your mind bending along with space-time, trying to visualize geometries that exist only in mathematics and in the fabric of reality itself. It is hard. The human brain evolved to navigate African savannas, not hyperbolic manifolds. But there is something beautiful in the effort, something deeply human about trying to picture the unpicturable. The edge of the universe in general relativity might not be an edge at all. It might be a horizon, a limit to what we can see rather than a limit to what exists. It might be a curvature, a gentle bending that turns the infinite into the finite without adding any boundaries. Or it might be something stranger still, a topological quirk that connects distant regions of space in ways that defy ordinary intuition. Einstein gave us the tools to ask these questions properly. He did not give us the answers. Those are still being worked out a century later, but he opened the door to a universe far stranger and more wonderful than Newton's infinite stage. The stars above you are curving space with their mass right now, sending ripples of gravity across the cosmos, shaping the geometry you inhabit. And somewhere out there, at the edge of observation or the edge of existence, the shape of the universe is waiting to be discovered. You feel the universe beginning to move, not the individual stars and planets, they've been moving since the beginning, but space itself, the fabric that contains everything, stretching like taffy, pulling galaxies apart from each other in every direction. This is expansion, the discovery that transformed cosmology from philosophy into physics, and it changes everything about the question of edges. The year is 1929, and an astronomer named Edwin Hubble is staring at photographic plates and realizing something astonishing. The galaxies are running away from us. Not just a few of them, not just the nearby ones, but all of them, in every direction, and the farther away they are, the faster they are receding. It is as if the universe itself is inflating, carrying the galaxies along for the ride. Hubble was not the first to notice hints of this expansion. A few years earlier, the Belgian priest and physicist Georges Lemaitre had proposed that the universe was expanding, based on his solutions to Einstein's equations. But Lemaitre's work was largely ignored until Hubble provided the observational evidence. The redshifts were unmistakable. The light from distant galaxies was stretched toward the red end of the spectrum, exactly what you would expect if those galaxies were moving away from us. And the relationship between distance and speed was remarkably consistent. Twice as far meant twice as fast. This ratio, now called the Hubble constant, became one of the fundamental parameters of cosmology. Here is what makes expansion so mind-bending. The galaxies are not moving through space. Space is moving them. Imagine dots on a balloon being inflated. The dots are not crawling across the surface. They are staying put while the surface itself stretches, increasing the distance between every pair of dots. In the same way, galaxies are mostly stationary in their local regions of space, but the space between them is growing, and that growth carries them apart. This distinction matters enormously for the question of edges. In Newton's universe, if you travelled fast enough in one direction, you might eventually reach a boundary, a place where matter thinned out and space became truly empty. But in an expanding universe, the boundary is receding faster than you can approach it. The edge, if there is one, is running away from you at an ever-increasing speed. And here is where things get truly strange. In an expanding universe, there are regions of space that we can never reach, never see, never interact with, not because they are behind a wall, but because the expansion carries them away faster than light can travel. Yes, faster than light. This does not violate relativity, because nothing is moving through space faster than light. Space itself is expanding, and there is no speed limit on that. The galaxies on the far side of the observable universe are not breaking any laws. They are just being carried away by the relentless growth of the cosmos. Historians still argue about when exactly the implications of expansion fully sank in. Hubble himself was cautious, preferring to describe his observations in neutral terms and letting others draw the cosmological conclusions. Lemaitre was bolder, proposing that if the universe was expanding now, it must have been smaller in the past, and if you ran the clock backward far enough, you would reach a moment when everything was compressed into a single point, what he called the primeval atom, and what later generations would call the Big Bang. Here is a quirky fact that might surprise you. The Big Bang theory was initially derided as religious nonsense by some secular scientists, precisely because it seemed to support the idea of creation. The steady-state theorists, led by Fred Hoyle, proposed instead that the universe had always existed in more or less its current state, with new matter constantly being created to fill the gaps left by expansion. Hoyle actually coined the term Big Bang as an insult, mocking the idea of a cosmic beginning. But the evidence eventually piled up in favour of the Big Bang, and the steady-state theory faded into history, taking Hoyle's hopes for an eternal universe with it. The expansion of the universe also resolves Olber's paradox more completely than the finite age argument alone. Remember, the problem was that an infinite universe with infinite stars should produce an infinitely bright sky. The finite age of the universe helps, because light from the most distant stars has not reached us yet. But expansion adds another effect. As light travels across expanding space, it gets stretched, its wavelength increasing, its energy decreasing. Light from the most distant galaxies has been stretched so much that it has shifted out of the visible spectrum entirely, becoming infrared or microwave radiation. This cosmic redshift dims the distant universe, making the night sky darker than it would otherwise be. You're riding this expansion right now without feeling it. The space between the atoms in your body is not expanding. Local gravity and electromagnetic forces hold things together. But the space between galaxies is growing, and the rate of growth is accelerating, as we'll discuss later. The universe is getting bigger, which means the edge, if there is one, is getting farther away. Or maybe there is no edge. Maybe the expansion is happening everywhere, in an infinite universe, with no boundary and no center. Every point sees every other point receding, and no point is special. This is the cosmological principle, the assumption that the universe looks roughly the same from every location. No center, no edge, just an endless expanse of expanding space, with galaxies scattered throughout. But what about the beginning? If the universe had a beginning, does that mean it started from an edge, a point, a singularity? The Big Bang is often described as an explosion, but that metaphor is misleading. It was not an explosion into space, it was an explosion of space. There was no outside for the explosion to expand into. Space and time themselves came into existence, or at least into the form we can understand at that moment. The edge of the universe in this sense is not out there in space, it is back there in time, at the beginning. You feel yourself relaxing into this expanding cosmos, letting the galaxies drift apart around you. The night is quiet, but the universe is humming with motion, stretching and growing in every direction. The edge is far away, or there is no edge, or the edge is the beginning itself, a moment 13.8 billion years in the past. The questions multiply as fast as the space. You're about to meet a boundary, but it is not the kind you might expect. It is not a wall or a fence or a curtain. It is a horizon, a limit to what you can see, and understanding it is essential to understanding what we mean when we talk about the edge of the universe. The observable universe is a sphere centered on you. Not because you are special. Every observer everywhere in the cosmos has their own observable universe centered on them, but because light travels at a finite speed and the universe has a finite age. The farthest light that can have reached you since the beginning of time defines the edge of your observable universe. Beyond that edge, there may be more universe, almost certainly is more universe, but you cannot see it. The light has not had time to arrive. This observable universe has a radius of about 46 billion light years. You might think it should be 13.8 billion light years, matching the age of the universe, but expansion complicates things. The light from the most distant objects we can see left those objects when they were much closer to us. Since then, space has expanded, carrying those objects farther away, even as their ancient light continued its journey toward us. By the time the light arrives, the object that emitted it is now much more distant than the light travel time would suggest. This is called the particle horizon, and it is as close to an edge as most cosmologists are willing to talk about with confidence. Beyond the particle horizon, we have no direct information. No light, no gravitational waves, no cosmic rays, no signals of any kind have had time to reach us from those regions. They are causally disconnected from us, at least for now. Historians still argue about when the concept of the particle horizon was first clearly articulated. The mathematics was implicit in the early Big Bang models, but the explicit recognition of a cosmic horizon as a fundamental feature of the universe came later, as cosmologists worked out the implications of expansion in more detail. Today, the observable universe is one of the most precisely measured structures in science, its size and contents catalogued with remarkable accuracy. Here is a quirky fact that might shift your perspective. The observable universe contains roughly 2 trillion galaxies, each with an average of 100 billion stars, for a total of around 200 sextillion stars. That is a 2 followed by 23 zeros, and this is just the observable part. The full universe, if it is infinite, contains infinitely more. If it is finite but very large, it still contains far more than we can see. Our little bubble of visibility is just a tiny fraction of whatever is out there. But here is the strange thing about the particle horizon. It is not fixed. It is growing. Every moment, light from slightly more distant regions reaches us for the first time. The edge of the observable universe is creeping outward, revealing new galaxies, new structures, new mysteries. In some sense, we're constantly discovering more universe, not by travelling, but simply by waiting. At the same time, the accelerating expansion of the universe is working against us. Galaxies that are currently visible will eventually cross what is called the event horizon, a different kind of boundary. The event horizon is not the farthest we can see, it is the farthest we can ever see. Once a galaxy crosses that threshold, the expansion of space will carry it away so fast that its light will never reach us, no matter how long we wait. The galaxy will fade from view, red-shifted into oblivion, as if it had fallen off the edge of the universe. This is not a distant theoretical worry. It is happening right now, in slow motion. Galaxies at the edge of the observable universe are already fading, their light stretched to longer and longer wavelengths. In the far future, trillions of years from now, distant galaxies will have vanished entirely, leaving our local group isolated in an apparently empty universe. Future astronomers, if there are any, might look up at a sky containing only the merged remains of the Milky Way and Andromeda, surrounded by perfect darkness, with no evidence that other galaxies ever existed. You let this sink in for a moment. The edge of the observable universe is not a wall you bump into. It is a horizon that recedes as you approach, reveals itself gradually over cosmic time, and will eventually shrink again as expansion isolates us from the rest of existence. It is an edge made of time as much as space, a boundary defined by the speed of light and the age of the cosmos. And what lies beyond this horizon? Here is where speculation begins, because by definition, we cannot observe it. Most cosmologists believe that the universe beyond our observable bubble looks pretty much like the universe within it. More galaxies, more stars, more void, more of the same. The cosmological principle suggests that no location is special, so there is no reason to think the unobservable universe is fundamentally different from the observable one. But we do not know. We cannot know, not with current physics. Some theorists have proposed that the universe beyond the horizon might have different properties, different physical constants, different laws. These ideas venture into speculative territory, and we'll explore some of them later. For now, just notice that the particle horizon is an edge of knowledge, not necessarily an edge of existence. You are sitting at the center of your own observable universe, surrounded by a sphere of light that has been traveling toward you since the beginning of time. Every direction you look, you are looking back in time, seeing the universe as it was when the light left. The most distant things you can see are also the oldest things you can see. Light from the cosmic dawn, the edge of visibility overlapping with the edge of time. This is your edge. This is the boundary of your cosmic neighborhood, and it is expanding right now as more light arrives, as the universe reveals more of itself to you. The edge is not a wall, it is a wave, washing over you from all directions, bringing news from the distant past and hinting at mysteries yet to come. You peer past the horizon now, into the territory that lies beyond what we can observe, and you find yourself in a realm of educated guesses and mathematical extrapolation. The universe does not end at the edge of visibility. The light simply has not had time to reach you yet, or, in the accelerating cosmos, it never will. But that does not mean there is nothing out there. Most cosmologists believe the universe extends far beyond our observable bubble, perhaps infinitely, perhaps merely unimaginably vast. This belief rests on the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. Homogeneous means the same everywhere. Isotropic means the same in every direction. No special locations, no preferred directions, no cosmic center, no cosmic edge. If the universe follows this principle, and all our observations so far suggest it does, at least within the observable region, then there's no reason to think it suddenly changes character just beyond the horizon. More space, more galaxies, more of the same. But how much more? Here is where the honest answer is, we do not know. The universe beyond the horizon could be finite, wrapping back on itself in some higher dimensional geometry, or it could be infinite, stretching endlessly in every direction. Both possibilities are consistent with current observations. The curvature of space, as best we can measure it, is very close to flat. So close that we cannot tell whether it is exactly flat, suggesting infinite extent, or very slightly curved, suggesting a closed finite cosmos. Historians still argue about when cosmologists first took seriously the possibility of a universe much larger than the observable region. In the early days of Big Bang cosmology, there was a tendency to treat the observable universe as if it were the whole thing, or at least the only part that mattered. But as measurements improved and the implications of expansion were worked out more carefully, it became clear that the observable universe was just a tiny window into something much larger. Here is a quirky fact that might boggle your mind. Some estimates, based on the measured flatness of space and the physics of cosmic inflation, suggest that the total universe is at least 250 times larger than the observable universe in every direction. That would make the total volume about 15 million times greater than the volume we can see, and that is a conservative estimate. The true figure could be far larger, or the universe could simply be infinite. If the universe is infinite, it contains some very strange things. In an infinite universe obeying the laws of probability, every possible configuration of matter eventually occurs somewhere. This means there are regions of space where another Earth exists, with another you, living a life almost identical to yours. There are regions where history diverged at some critical moment, creating alternate versions of everything. There are regions where the atoms have arranged themselves into patterns we cannot imagine, civilizations we cannot conceive, wonders and horrors beyond counting. This is not science fiction. It is a straightforward consequence of infinity. If there are infinitely many chances for particles to arrange themselves, and the laws of physics allow for your particular arrangement, then your arrangement will happen again. Many times, infinitely many times, the uniqueness you feel, the specialness of your existence, dissolves in the acid bath of infinity. Some people find this idea disturbing, others find it liberating. If there are infinite copies of you, making every possible choice, then in some sense every path is taken, every story is told, every outcome is real somewhere. The choices you make here matter to you in your corner of infinity. but they are also being unmade and remade endlessly in regions so distant that their light will never reach you. Of course, this assumes the universe is actually infinite, which remains unproven. It also assumes the laws of physics are the same everywhere, which is another assumption we cannot verify beyond the horizon. The universe might surprise us. It often does. What we can say with more confidence is that the observable universe is not the whole story. The particle horizon is not a boundary of existence, but a boundary of perception. Beyond it lies more space, almost certainly, and probably more matter, more structure, more of everything we see within our bubble. The edge of observation is not the edge of reality. This has profound implications for the question we started with. Can the universe be infinite and still have an edge? If the universe is infinite, there is no edge in the traditional sense, no wall, no boundary, no place where space gives way to not space. But there are horizons, limits to what we can know, boundaries created by the finite speed of light and the accelerating expansion of space. These horizons are edges of a sort, separating the knowable from the unknowable, the accessible from the forever out of reach. You float in this conceptual space, surrounded by your bubble of visibility, aware that the bubble is embedded in something vastly larger. The stars you see are just the nearby neighbours. The galaxies you photograph are just the local cluster. Beyond, stretching in every direction, is more universe than you could explore in 1 trillion lifetimes, more space than light itself can cross before the expansion carries it away. The edge is not a place. The edge is a condition of your existence, a limit built into the structure of space-time and the physics of light. You will never reach it, never touch it, never stand at the boundary and look out at what lies beyond. But you can know that something lies beyond, even if you cannot see it. The universe is bigger than your vision, and that is perhaps the most humbling fact of all. You're about to twist your brain into a pretzel, and you're going to enjoy it. The universe is not just vast. It might also be strangely connected, folded in on itself in ways that make the concept of edge almost meaningless. This is the realm of cosmic topology, where mathematicians and physicists ask not just how big the universe is, but what shape it has. Start with something simple. Imagine you are playing a video game, one of those classic arcade games where the screen wraps around. You fly your little spaceship off the right edge, and you reappear on the left. You fly off the top and you come back from the bottom. The screen is finite, it has a definite size, but there are no edges in the usual sense. You cannot get stuck at a boundary because there is no boundary. The topology of the space connects opposite edges, turning a finite rectangle into a closed surface. Now imagine the same thing in 3 dimensions. You fly your spaceship in one direction, far enough, and eventually you return to where you started. Not because space curves back on itself like the surface of a sphere, but because the topology identifies distant points. You leave through one wall and enter through another seamlessly without ever encountering an edge. This kind of topology is called a torus in 2 dimensions, and it generalizes to higher dimensions in ways that mathematicians find delightful and everyone else finds headache-inducing. The important point is that a universe could be flat, Euclidean, no curvature, and still be finite because of topology. The geometry is local, describing how space curves or does not curve in your immediate neighborhood. The topology is global, describing how different regions of space connect to each other. Historians still argue about when topology entered cosmology as a serious concern. The mathematics has been around for over a century, but the application to the real universe gained traction more recently, as precision measurements of the cosmic microwave background allowed cosmologists to search for evidence of wraparound. Here is how you might detect a closed topology. If the universe wraps around in some direction, light from distant sources could reach you by multiple paths, the direct route and the wraparound route. You might see the same galaxy in two different places on the sky, or you might notice repeated patterns in the cosmic microwave background, echoes created by the finite size of the universe. Cosmologists have searched for these signatures, and so far they have not found any convincing evidence. This does not prove the universe is infinite. It just means that if the universe is finite, it is very large, large enough that the wraparound is beyond our observable horizon. Here is a quirky fact that might intrigue you. One of the topologies that cosmologists have seriously considered is called the Poincaré dodecahedral space, named after the famous mathematician Henri Poincaré. In this topology, the universe has the shape of a 12-faced polyhedron, a dodecahedron with opposite faces identified. If you exit through one pentagonal face, you re-enter through the opposite face, rotated by 36 degrees. It is a closed, finite space with no edges, and it would produce specific patterns in the cosmic microwave background that have been searched for, so far without success. The search for cosmic topology is ongoing. New data from improved telescopes and satellites continues to tighten the constraints, pushing the minimum size of a closed universe larger and larger. If the universe does wrap around, it does so on scales that dwarf the observable universe, making direct detection extremely difficult. But even without detection, the possibility matters for our question. Can the universe be infinite and still have an edge? If the universe has non-trivial topology, it might be finite but edgeless, a closed space where every point is interior, where you can travel forever without hitting a boundary, but eventually return to your starting point. The edge, in this scenario, simply does not exist. There's no outside, no boundary, no limit, just space, connecting to itself in a seamless loop. Or the universe might be truly infinite, with trivial topology, stretching out forever in every direction without wrapping around. In this case, there is also no edge, just more and more space, galaxies beyond galaxies, voids beyond voids, endlessly. Or, and this is where things get speculative, the universe might have edges in some sense, boundaries where the topology ends or where different regions with different properties meet. These are not well understood possibilities, and they venture into the frontier of theoretical physics, but they cannot be ruled out. You breathe slowly, letting the topological possibilities settle into your mind. The universe might be a sphere, a torus, a dodecahedron, or something far stranger. It might be infinite, or finite, or something that does not fit either category. The shape is hidden from us, encoded in the patterns of light that we're only beginning to decode. And through all of this, the question of edges remains tantalizingly open. Topology gives us new ways to think about boundaries, new ways to imagine a universe that is limited but unbounded, finite but seamless. The edge you're looking for might not be out there in space. It might be a property of how space itself is stitched together, a global feature that only becomes apparent when you travel far enough or look closely enough at the oldest light. The night is deep now, and your thoughts are deep with it. The universe is folding around you, or not, connecting to itself, or not, infinite or finite or something in between. The edge is somewhere or nowhere, waiting for the right question to reveal itself. You're listening to the oldest light in the universe now, a faint whisper that has been travelling for 13.8 billion years, almost since the beginning itself. This is the cosmic microwave background, and it holds clues to everything. The age of the universe, its contents, its geometry, its shape. If the universe has an edge, or curves back on itself, or wraps around in strange topologies, the cosmic microwave background might be the place to find the evidence. The cosmic microwave background, CMB for short, is the afterglow, the Big Bang. In the early universe, everything was hot, dense, and opaque. Photons could not travel far before scattering off free electrons, creating a brilliant fog that filled all of space. But about 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral atoms. Suddenly the fog lifted. Photons could travel freely, streaming in all directions, carrying information about the conditions at that moment. Those photons have been travelling ever since, stretched by the expansion of the universe from visible light to microwave radiation. When you tune a television to a channel with no signal, a small percentage of the static you see is actually cosmic microwave background, ancient light from the edge of time mixing with modern electronic noise. You've been watching the birth of the universe your whole life without knowing it. The CMB is almost perfectly uniform, the same temperature in every direction to within 1 part in 100,000. This uniformity is powerful evidence for the cosmological principle, confirming that the universe was homogeneous and isotropic at that early epoch. But embedded in the uniformity are tiny fluctuations, slight variations in temperature that correspond to slight variations in density. These fluctuations are the seeds of all structure: galaxies, clusters, superclusters, the cosmic web. Where the early universe was slightly denser, matter eventually collected, pulled together by gravity into the structures we see today. Historians still argue about the exact moment when the significance of the CMB was fully appreciated. It was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate noise from a radio antenna, and kept finding a persistent hum that seemed to come from everywhere. They eventually realized they were detecting the cosmic microwave background, a discovery that earned them the Nobel Prize and confirmed the Big Bang theory in a way that no previous observation had. Here is a quirky fact. When Penzias and Wilson first encountered the mysterious noise, they suspected it might be caused by pigeon droppings accumulated in their antenna. They cleaned the antenna thoroughly, but the noise persisted. It was not pigeon droppings, it was the echo of creation itself. The CMB is a snapshot of the universe when it was only 380,000 years old, an infant cosmos just beginning to emerge from its hot, dense infancy. By studying the patterns in this snapshot, cosmologists can learn about the conditions at that time, and by extrapolating backward and forward, they can reconstruct the history of the universe. One of the key things the CMB reveals is the geometry of space. The fluctuations in the CMB have a characteristic size, corresponding to the largest regions that were in causal contact at the time of recombination. This size acts like a standard ruler, allowing cosmologists to measure how space has curved or stretched since then. If space is positively curved, like the surface of a sphere, the apparent size of the fluctuations would be larger than expected. If space is negatively curved, like a saddle, the apparent size would be smaller. If space is flat, the size would match the theoretical prediction exactly. The measurements, refined over decades by satellites like COBE, WMAP and Planck, show that space is flat to within the precision of our instruments. The fluctuations are exactly the size they should be in a flat universe. This does not prove the universe is infinite. A flat universe could still be finite if it has a non-trivial topology, but it rules out strong curvature, closing off one of the possible ways the universe might be bounded. The CMB also constrains topology. If the universe wrapped around in some direction, we would expect to see repeated patterns, matching circles on opposite sides of the sky. Cosmologists have searched for these circles and found none, which means that if the topology is non-trivial, the scale of the wraparound is larger than the observable universe. We're not seeing the same regions from multiple angles. Every direction shows us unique territory. You let the ancient light wash over you, metaphorically speaking. The CMB is everywhere, filling all of space, a relic of the moment when the universe became transparent. It has been travelling toward you since before the Earth existed, before the sun ignited, before the Milky Way formed, and it carries a message. The universe is flat, or very nearly so, and if there are edges or curvatures or topological quirks, they're hidden beyond the horizon, out of reach. This is both reassuring and frustrating. The CMB tells us so much, but it cannot tell us everything. The edge of the universe, if it exists, is either very far away or of a kind that the CMB cannot reveal. We are left with constraints, limits, boundaries on our ignorance. The universe is not strongly curved. The universe does not wrap around on observable scales. Beyond that, we can only guess. The night is quiet and the microwave sky is invisible to your eyes but present all around you. A bath of ancient photons that have seen more of the universe than any telescope ever will. They are the oldest messengers, and their message is one of deep mystery. The cosmos is vast, flat, and full of secrets we are only beginning to uncover. You're about to go back further than you have ever gone, to the first fraction of a second after the Big Bang, when the universe underwent an event so dramatic and so brief that it defies ordinary comprehension. This is inflation, the hypothetical period of exponential expansion that may have shaped everything we see today, and that may have pushed any true edge of the universe unimaginably far away. The standard Big Bang model has a problem, several problems actually, and inflation was invented to solve them. One problem is called the horizon problem. Look at the cosmic microwave background, and you see the same temperature everywhere in every direction to extraordinary precision. But here is the puzzle. Regions on opposite sides of the CMB sky were never in causal contact. Light, travelling at the fastest possible speed, did not have time to pass between them before the CMB was released. How did they end up at the same temperature if they could not exchange information? The answer, according to inflationary theory, is that they were in contact, but much earlier, before inflation. The region that became our observable universe was once incredibly tiny, small enough that light could cross it easily, small enough that every part could reach thermal equilibrium with every other part. Then inflation happened. Space expanded exponentially, faster than light, stretching that tiny uniform patch into something vast. Regions that had been neighbours were suddenly separated by enormous distances, carried apart by the explosive growth of space itself. Inflation solves other problems too. It explains why the universe is so flat. Exponential expansion drives any curvature towards zero, like inflating a balloon until the surface looks flat. It explains why we do not see exotic relics like magnetic monopoles, which some theories predict should have formed in the early universe. Inflation dilutes them to undetectable densities, and it provides a mechanism for generating the tiny fluctuations in the CMB, quantum fluctuations in the inflationary field that were stretched to cosmic scales and eventually seeded the formation of galaxies. Historians still argue about the exact status of inflation. It is widely accepted but not proven. The evidence is circumstantial. Inflation predicts a flat universe, and we observe a flat universe. Inflation predicts a specific pattern of fluctuations, and we observe something close to that pattern. But there are alternative theories that also fit the data, and inflation itself comes in many varieties, each with slightly different predictions. Here is a quirky fact that might startle you. During inflation, the universe may have expanded by a factor of at least 10 to the 26th power in less than a trillionth of a trillionth of a trillionth of a second. That is an increase of over 78 orders of magnitude in a time so brief that it makes the blink of an eye seem like a geological epoch. The scale of inflation is almost impossible to grasp. And here is the implication for edges. If inflation really happened, it pushed the true boundary of the universe, if there is one, so far away that it is utterly irrelevant to anything we can observe. Before inflation, the universe might have been finite, a tiny bubble of space-time with actual edges. After inflation, those edges are so distant that the observable universe is just an infinitesimally small patch of a vastly larger whole. Some versions of inflation go even further, proposing that inflation is not a one-time event but an ongoing process. In eternal inflation, most of the universe is always inflating, with occasional regions dropping out of inflation to become pocket universes like ours. Each pocket universe has its own Big Bang, its own history, its own physical laws possibly. The totality of existence in this picture is a vast inflating multiverse, with our observable universe as just one bubble among uncountably many. In this scenario, the question of edges becomes almost meaningless. Our universe has a horizon, a limit to what we can see, but beyond that horizon is more of our pocket universe, and beyond that is the inflating bulk, and beyond that are other pocket universes, and the whole structure continues indefinitely. There is no edge in any meaningful sense, just more and more space-time, inflating eternally, spawning new bubbles forever. This is speculative, of course. Eternal inflation is a theoretical possibility, not an observational fact. We have no way to see other pocket universes or detect the inflating bulk directly. But the possibility is tantalizing, suggesting that the universe we know is just a tiny corner of a much larger reality, and that the concept of an edge might be fundamentally misguided. You breathe deeply, letting the enormity of inflation settle into your awareness. In less than the time it takes a photon to cross an atom, the universe may have expanded from something smaller than a proton to something larger than the observable universe is today. Whatever edges existed before inflation were erased, pushed beyond the horizon, rendered undetectable by the very mechanism that made the universe hospitable to life. The edge, if it exists, is not just far away. It is so far away that the entire history of the universe since inflation has not been enough time for its influence to reach us. The observable universe is a tiny island of accessibility in an ocean of inaccessible vastness, separated from any boundary by distances that beggar imagination. And yet within this island we can still ask questions. We can still wonder. We can still peer at the oldest light and try to read the story of our origins. Inflation may have pushed the edge beyond reach, but it has not extinguished the curiosity that drives us to look for it. You're wandering now into territory where physics becomes philosophy, and speculation becomes almost indistinguishable from imagination. The multiverse. The idea that our universe is not alone, that beyond the horizon, beyond the inflating bulk, beyond everything we can ever hope to observe, there are other universes, each with its own properties, its own history, its own edges or lack thereof. The multiverse is not a single theory, but a collection of related ideas, arising from different branches of physics and converging on a similar conclusion. The totality of existence is far larger and stranger than any single universe. Some versions emerge from eternal inflation, as we discussed. Others arise from string theory, which allows for a vast landscape of possible physical laws, each realized in its own universe. Still others come from quantum mechanics, in the many worlds interpretation, where every quantum measurement branches reality into multiple coexisting outcomes. Let us focus on the cosmological multiverse, the one that connects most directly to our question about edges. In eternal inflation, most of the universe is always inflating, expanding exponentially. But quantum fluctuations occasionally cause small regions to stop inflating and undergo their own big bangs, becoming pocket universes. Each pocket universe is isolated from the others by the inflating bulk, which expands so fast that signals can never travel between bubbles. Each universe is an island, causally disconnected from all the others. In this picture, our universe has edges in a strange new sense. The boundary of our pocket universe is not a wall, but a transition region, where the local physics changes and the inflating bulk begins. We cannot reach this boundary because the space between us and it is expanding faster than we could ever travel. We cannot see it, because no light from beyond it could ever reach us. But it exists in some sense, an edge defined by the end of our particular cosmic history and the beginning of something else. Historians still argue about whether the multiverse should be considered science at all. It makes predictions, sort of, but those predictions may be untestable in principle, since we cannot observe other universes directly. This has led to heated debates about the nature of scientific knowledge and the boundaries of empirical inquiry. Some physicists embrace the multiverse as the natural conclusion of our best theories. Others reject it as untestable speculation, a flight of mathematical fancy that has departed from the solid ground of observation. Here is a quirky fact that might intrigue you. In some multiverse models, every possible universe exists. Every combination of physical constants, every configuration of initial conditions, every outcome of every quantum measurement. All of them are realized somewhere in the infinite ensemble. This is called the Level 4 multiverse, proposed by cosmologist Max Tegmark, and it is perhaps the most extreme version of the idea. In this picture, mathematical existence equals physical existence. If a universe is logically consistent, it exists. If every possible universe exists, then asking about the edge of the universe becomes asking about the edge of possibility itself. And possibility, if we define it as logical consistency, has no edge. Every consistent configuration is realized. The multiverse is infinite not just in space but in variety, containing universes with different dimensions, different forces, different flows of time. Somewhere there is a universe where time runs backward. Somewhere there is a universe where gravity repels instead of attracts. Somewhere there is a universe where you made every different choice you could have made, living every different life you could have lived. This is dizzying, and it is meant to be. The multiverse takes the question of edges and explodes it, turning a spatial question into a metaphysical one. There is no edge to the multiverse because there is no outside to the set of all possibilities. The edge is not out there in space. It is not even in principle locatable, because any location you could specify is within some universe or another. Of course, this might all be wrong. The multiverse might not exist. Eternal inflation might be incorrect. String theory might be a dead end. And the many worlds interpretation might be a misunderstanding of quantum mechanics. We simply do not know. The multiverse is a possibility that our best theories suggest, but it is not confirmed, and it may never be. What matters for our question is the way the multiverse reframes the idea of edges. In a single, finite universe, an edge is a boundary between existence and non-existence, between something and nothing. In a multiverse, there is no nothing. There is always more space, more time, more possibilities, more universes. The edge is not where existence ends. It is where one kind of existence gives way to another. You float in this sea of possibilities, feeling the weight of infinity pressing in from all directions. The edge of the universe, the edge of the multiverse, the edge of existence itself, they blur together, dissolve, become something other than edges. The question you started with is transforming, becoming less about location and more about limits, less about walls and more about knowledge. The multiverse is a concept for staying awake, perhaps, for nights when the questions are too big and the answers are too small. Tonight, you are drifting towards sleep, and the multiverse can wait. But it is out there, or in here, or everywhere, a reminder that the universe we know might be just the beginning of the story. You're face to face now with infinity itself, that slippery concept that has haunted this entire journey. Philosophers have wrestled with it, mathematicians have tamed it somewhat, and physicists have used it as a tool while remaining deeply uncertain whether it actually exists out there in the physical world. Can something infinite be real? Can the universe stretch on forever and still be a coherent, concrete thing? The mathematical infinity is well behaved, in its strange way. Georg Cantor, the 19th century mathematician, showed that there are different sizes of infinity, a hierarchy of infinities that can be compared, added, multiplied, and manipulated according to consistent rules. The infinity of counting numbers is smaller than the infinity of real numbers, which is smaller than the infinity of possible functions, and so on, climbing a ladder of infinities that has no top rung. Mathematically, infinity is not a single thing, but a family of things, each larger than the last. But physical infinity is more troublesome. When physicists' equations produce infinite answers, it is usually a sign that something has gone wrong, that the theory is breaking down or being applied beyond its domain of validity. Infinite densities, infinite energies, infinite temperatures, these are signals of ignorance, not descriptions of reality. The singularity at the centre of a black hole, for instance, is often described as having infinite density. But most physicists believe this is an artifact of incomplete theory, a placeholder for physics we do not yet understand. So what about the infinity of space? Can the universe actually extend forever, with an infinite number of galaxies, an infinite amount of matter, an infinite volume of void? Some cosmologists are comfortable with this possibility. The mathematics allows it, the observations are consistent with it, and there is no obvious contradiction in an infinite universe. Others are more skeptical, suspicious that physical infinity is always a sign of incompleteness, a boundary we have not yet learned to cross. Historians still argue about the origin of this skepticism. Some trace it back to Aristotle's rejection of actual infinity. Others point to the paradoxes that arise when you try to apply ordinary intuitions to infinite collections. Hilbert's Hotel, for instance, where a fully occupied hotel with infinitely many rooms can always accommodate one more guest by shifting everyone up one room. These paradoxes do not show that infinity is impossible, but they do show that infinity requires careful handling. Here is a quirky fact that might amuse you. The philosopher Immanuel Kant argued that the question of whether the universe is finite or infinite is unanswerable, one of the antinomies of pure reason, where equally compelling arguments can be made on both sides. Kant thought this showed the limits of human rationality, the places where our concepts cannot reach. Modern physicists are more optimistic. We have mathematical tools that can't lacked, but the fundamental tension remains. If the universe is truly infinite, certain strange consequences follow. As we discussed earlier, every possible configuration of matter eventually recurs somewhere in an infinite space. There are infinitely many copies of you, of Earth, of the entire observable universe. This is not a metaphor but a mathematical implication of infinity, combined with a finite number of ways particles can arrange themselves in a finite region. The uniqueness you feel is local. Globally, you are replicated endlessly. Some people find this disturbing. The idea that you are not special, that there are infinitely many yous making infinitely many choices, can feel like an assault on meaning and significance. Others find it liberating, a reminder that the universe is larger than human ego, and that existence extends beyond any individual's comprehension. But here is the deeper point. If the universe is infinite, there is no edge. Not in any direction, not at any distance. You could travel forever and never reach a boundary. The question, what lies beyond the edge, has no answer because there is no beyond. Infinity swallows the concept of boundary entirely. And yet, there are still horizons. The particle horizon, the event horizon, the limits of observation. These are edges of a kind, boundaries of knowledge rather than boundaries of existence. You can talk about the edge of the observable universe even if the total universe is infinite. You can talk about the edge of causal contact, the farthest region that can ever influence you, even if space stretches on without limit. So the question, can the universe be infinite and still have an edge, gets a nuanced answer. If by edge you mean a physical boundary, a wall where space ends, then no, an infinite universe has no such boundary. But if by edge you mean a horizon, a limit to interaction, a boundary of access, then yes, even an infinite universe has edges in this sense. The edge is not out there, it is between you and the out there, a property of your relationship to the cosmos rather than a property of the cosmos itself. You let this distinction settle into your sleepy mind. The edge is relational, the edge is epistemological, the edge is the limit of your cosmic neighbourhood, not the limit of the universe. Beyond the edge, there is more universe, infinite more, but you will never see it, never touch it, never know it directly. The infinity is real, perhaps, but unreachable. The edge is close, perhaps, but not a wall. The night deepens and infinity hums quietly around you, incomprehensible and beautiful. You shrink down now, past the scale of galaxies, past the scale of stars and planets, past the scale of atoms and electrons, into the quantum realm where the very concept of edge begins to dissolve. Quantum mechanics is the physics of the very small, and it has strange things to say about boundaries, limits, and the nature of existence itself. In classical physics, objects have definite edges. A ball has a surface, a boundary between ball and not ball. You can measure where the ball ends and the air begins, but in quantum mechanics, particles do not have sharp boundaries. An electron around an atom does not orbit like a planet around the sun. It exists as a cloud of probability, a smear of possible locations that never quite terminates. The electron is most likely to be found in certain regions, but there is always a non-zero chance of finding it somewhere else, even very far away. The edge of the electron is fuzzy, grading off to infinity. This fuzziness extends to everything at the quantum level. Particles tunnel through barriers, appearing on the other side without ever quite being in between. Fields fluctuate even in empty space, producing virtual particles that pop into existence and vanish again before they can be directly observed. The vacuum is not empty but seething, a quantum foam of activity that blurs any distinction between something and nothing. Historians still argue about the implications of quantum mechanics for cosmology. The early universe was quantum mechanical through and through, its entire history governed by probabilities and uncertainties. Some physicists believe that the universe itself began as a quantum fluctuation, a tiny bubble of spacetime that inflated into everything we see. If this is true, the beginning of the universe was not a sharp edge but a fuzzy transition, a probabilistic emergence from quantum indeterminacy. Here is a quirky fact that might stretch your imagination. In some interpretations of quantum cosmology, the universe has no boundary in time either. Stephen Hawking and James Hartle proposed a model where the universe has no initial singularity, no moment of creation in the usual sense. Instead, time itself becomes space-like near the beginning, curving smoothly back on itself like the surface of a sphere. The universe is finite in age but has no temporal edge, no first moment. It simply is, a four-dimensional structure with no boundaries in space or time. This no-boundary proposal is elegant and controversial. It relies on mathematical techniques that push the boundaries of what physicists understand, and it makes predictions that are difficult to test. But it represents one of the most sophisticated attempts to grapple with the question of cosmic edges, suggesting that the very concept of a boundary might be incompatible with quantum mechanics at the deepest level. The quantum fuzziness of edges also affects the large-scale structure of the universe in subtle ways. The fluctuations in the cosmic microwave background, those tiny variations that seeded the formation of galaxies, began as quantum fluctuations during inflation. They were stretched to cosmic scales by the exponential expansion, but their origin was quantum, uncertain, probabilistic. The structure of the universe we see today is a magnified image of quantum randomness, painted across billions of light years. This connection between the very small and the very large is one of the most profound discoveries of modern cosmology. The universe is not just big, it is quantum. The rules that govern atoms also govern in some sense the entire cosmos. And those rules do not deal in sharp edges. They deal in probabilities, amplitudes, superpositions, entanglements, concepts that resist the clean distinctions of classical physics. So when you ask whether the universe has an edge, quantum mechanics offers a strange answer. Edges are not fundamental. They're approximations, conveniences, emergent features of a deeper reality that knows nothing of boundaries. At the quantum level, there is no sharp line between here and there, between something and nothing, between universe and not universe. There is only the wave function, spreading out to infinity, encompassing all possibilities, never quite reaching a terminus. This is not to say that the universe has no structure. It clearly does. Galaxies, clusters, voids, the cosmic web. But that structure emerges from underlying processes that are inherently fuzzy, probabilistic, boundless. The edge you're looking for might not exist in any fundamental sense. It might be a macroscopic illusion, a convenient fiction, a way of carving up the world that works at human scales but breaks down when you push too hard. You breathe slowly, feeling the quantum uncertainty humming in every atom of your body, in the air around you, in the distant stars. The edges are dissolving, softening, blurring into probability. The universe is not a box with walls. It is a wave, spreading, interfering, never quite ending, never quite beginning. The question of edges is becoming the question of how much resolution you can tolerate, how sharp you need your boundaries to be. Tonight you do not need them sharp, you can let them blur. You feel something strange now, a pressure that is not really a pressure, a force that is not really a force. It is dark energy, the mysterious something that fills all of space and is causing the expansion of the universe to accelerate. And it has profound implications for the question of edges, because dark energy is pushing the edge farther away, faster and faster, ensuring that most of the universe will forever remain beyond our reach. Dark energy was discovered in 1998, one of the most surprising findings in the history of astronomy. Two independent teams, studying distant supernovae to measure the rate of cosmic expansion, found that the expansion was not slowing down as everyone expected, but speeding up. The universe was not gently coasting after the Big Bang, it was flooring the accelerator, flying apart with increasing velocity. This acceleration requires something to drive it, some form of energy that pervades all of space and exerts a kind of anti-gravity, pushing things apart rather than pulling them together. We call it dark energy because we do not know what it is. It is dark in the sense of being hidden, mysterious, unknown. It makes up about 68% of the total energy content of the universe, yet we have no fundamental understanding of its nature. Historians still argue about how surprised the community really was. Some physicists had anticipated the possibility of accelerating expansion based on theoretical considerations, particularly the cosmological constant that Einstein had introduced and then abandoned. Others were genuinely shocked, their worldviews upended by data that contradicted decades of expectation. The Nobel Prize awarded in 2011 recognized the magnitude of the discovery. Here is a quirky fact that might unsettle you. The simplest explanation for dark energy is that empty space has a small but non-zero energy density, a kind of intrinsic restlessness that pushes outward. Quantum field theory predicts that the vacuum should have such an energy, but the predicted amount is outrageously, absurdly, hilariously wrong, off by a factor of about 10 to the 120th power. This discrepancy, sometimes called the worst prediction in physics, suggests that we are missing something fundamental about the nature of space, time, and energy. The implications of dark energy for cosmic edges are sobering. In a universe with accelerating expansion, the event horizon, the boundary beyond which light can never reach us, shrinks over time. Galaxies that are currently visible will eventually cross that horizon and disappear from view. Their light will be redshifted to infinity, stretched to wavelengths so long that no detector could ever register them. One by one, the distant galaxies will wink out, not because they are ceasing to exist, but because the space between us and them is expanding too fast for their light to keep up. In the far future, trillions of years from now, our local group of galaxies, the Milky Way, Andromeda, and their smaller companions, will have merged into a single giant elliptical galaxy. But all the other galaxies will have vanished beyond the event horizon, their light unable to reach us, their existence invisible. Future astronomers in that distant era, if any exist, will look out at a universe that appears almost empty, a single galaxy surrounded by perfect blackness. They will have no evidence that other galaxies ever existed, no way to infer the expansion of the universe, no access to the cosmic microwave background, which will have redshifted to undetectable wavelengths. The edge of their observable universe will have contracted to essentially nothing beyond their own galactic shores. This is a kind of cosmic loneliness that is hard to contemplate. The universe is not just big, it is destined to become apparently small, at least from the perspective of any observers who remain. The edge is not just far away, it is actively receding, pulling the carpet out from under our feet, erasing the evidence of cosmic history. Dark energy might have other implications too, depending on its true nature. If dark energy is constant, as current observations suggest, the accelerating expansion will continue forever, isolating our local group in an ever-expanding void. But if dark energy changes over time, becoming stronger, it could eventually tear apart galaxies, stars, planets, atoms, a scenario called the Big Rip. In that case, the edge would not recede, it would come for you, ripping through every scale of existence until nothing coherent remains. This is probably not going to happen. The Big Rip requires a specific kind of dark energy that current observations do not favour. But it remains a logical possibility, a reminder that the question of edges is not settled, that the fate of the universe depends on physics we do not yet understand. You relax into this accelerating cosmos, feeling the distant galaxies slipping away, the edge of visibility creeping closer even as the universe grows. The night is dark, and it will get darker. But for now, you can still see the stars, still wonder about what lies beyond, still ask questions that reach farther than any light ever will. You find yourself in a room full of very smart people, and they are arguing. This is the nature of academia, of course, but this particular argument has been going on for centuries and shows no signs of resolution. The question, can an infinite universe logically have any kind of edge? The philosophers and physicists are still disagreeing, and their disagreement illuminates something deep about the limits of human understanding. The philosophical tradition has always been suspicious of infinity. We encountered Aristotle earlier, with his distinction between potential and actual infinity. That distinction lives on in modern debates, where some philosophers argue that actual infinities cannot exist in the physical world, only in mathematics. On this view, The universe must be finite, even if it is very large, because an actually infinite collection of things leads to paradoxes and contradictions. Consider Hilbert's hotel again. If the hotel is full and a new guest arrives, you can make room by moving everyone up one room. Guest in room 1 moves to room 2, guest in room 2 moves to room 3, and so on, forever. The new guest moves into room 1. This seems to violate the ordinary logic of full, and some philosophers argue it shows that actual infinities are absurd, that they do not play by the rules that govern finite collections. But other philosophers push back. The paradoxes of infinity, they argue, are paradoxes only if you insist on applying finite intuitions to infinite cases. Hilbert's hotel is not contradictory. It is just surprising. The rules for infinite collections are different from the rules for finite ones, but they are consistent rules, and there is no logical barrier to an actually infinite universe. Historians still argue about who has the better of this debate. The question cuts deep into metaphysics, touching on the nature of existence, the structure of reality, and the limits of human reason. It is not the kind of question that can be settled by experiment, at least not directly, which is why it remains open after millennia of discussion. Here is a quirky fact that might amuse you. The mathematician David Hilbert, who invented the hotel thought experiment, was actually defending the coherence of actual infinity, not attacking it. He wanted to show that infinite collections could be reasoned about consistently, even if they behaved strangely. The paradoxes were features, not bugs, demonstrations of the richness of infinite mathematics. Now, what about edges? If the universe is infinite, can it still have an edge? Logically, this seems contradictory. An edge is a place where something ends, and infinity means something does not end. But as we have seen, the concept of edge is slipperier than it first appears. There are horizons, limits of observation that function like edges without being physical boundaries. There are topological wraps, where space connects back to itself without terminating. And there are transitions, regions where one kind of existence gives way to another, as in the multiverse scenario. Physicists and philosophers handle this ambiguity in different ways. Physicists tend to be pragmatic, defining terms operationally based on what can be measured or observed. The particle horizon is an edge for practical purposes, even if it is not a wall. The event horizon is a boundary for causal interaction, even if space continues beyond it. Physicists are comfortable with multiple kinds of edges, each meaningful in its own context. Philosophers, by contrast, tend to push for precision, asking what we really mean by edge and whether our concepts are coherent. Can a boundary exist without something on the other side? Can space end without there being a non-space beyond? These questions do not have easy answers, and the philosophical literature is full of competing intuitions and rival frameworks. The disagreement extends to the nature of space itself. Is space a substance, a thing that exists independently of the objects within it? Or is space merely a set of relations between objects, with no independent reality? If space is substantial, it might make sense to ask where it ends. If space is relational, the question might be ill-formed. Space just is wherever objects are, and where there are no objects, there is no space to end. These debates are not merely academic. They influence how cosmologists interpret their data and construct their models. The assumption that the universe has no edge, the cosmological principle, is partly a philosophical stance, a choice about what kinds of models are worth considering. If you reject that assumption, different models become possible, and the question of edges opens up in new ways. You listen to the arguing voices, the philosophers and physicists talking past each other and occasionally connecting, making progress and then losing ground. The question is not settled. It may never be settled, at least not in the way that ordinary questions get settled. But the conversation itself is valuable, a collective attempt to push human understanding towards something it may not be able to fully grasp. The edge of the universe, if it exists, is also the edge of our concepts, the place where familiar ideas stop working and new ones have not yet been invented. You're at that edge now, in a sense, pushing your sleepy mind against the limits of what can be thought. You're going on a journey now, an impossible journey, a thought experiment that takes you to the edge of the universe, or as close as you can imagine getting. You're travelling outward, past the Earth, past the solar system, past the Milky Way, past the local group, past the great clusters and superclusters, into the depths of intergalactic space, toward the horizon and whatever lies beyond. The journey is impossible for several reasons. First, the distances are too vast. The edge of the observable universe is 46 billion light-years away, and travelling at any subliminal speed would take far longer than the current age of the universe to reach it. Second, the universe is expanding and the expansion is accelerating, so the edge is receding faster than you could ever approach it. Third, there might not be an edge to reach. Space might continue indefinitely, or wrap around, or dissolve into quantum foam, or transition into something else entirely. But thought experiments are not bound by physical constraints. So imagine you have a magical ship, a vessel that can travel as fast as you like, ignoring the speed of light, ignoring the expansion of space, heading straight for the boundary. What would you find? In an infinite universe with no edge, you would find more of the same. Galaxies upon galaxies, voids upon voids, the cosmic web repeating endlessly in every direction. No matter how far you travelled, there would always be more space ahead, more matter, more structure. You would never reach a wall, never bump into a barrier, never find a sign that says universe ends here. The journey would be endless, literally, with no terminus. Historians still argue about whether this picture is satisfying or disturbing. Some people find comfort in the idea of infinite extension, a universe without limits, full of endless possibilities. Others find it vertiginous, even nauseating, a cosmos too big to comprehend with no edges to give it shape or meaning. Here is a quirky fact that might give you pause. If you travelled far enough in an infinite universe, you would eventually encounter regions that look exactly like the observable universe, down to every detail. Not just similar galaxies and similar structures, but identical copies, atoms in the same positions, photons following the same paths, histories unfolding in the same ways. This is not speculation. It is a mathematical consequence of infinity. In an infinite universe with finite configurations, every configuration recurs. You would find other Earths, other yous, other versions of this exact moment, repeated endlessly. Now imagine a different scenario. Suppose the universe is finite, closed, wrapping back on itself like the surface of a hypersphere. What happens when you travel toward the edge? There is no edge to reach. You travel, and eventually you start to recognize things. That galaxy looks familiar. That cluster. Have you seen it before? You're approaching your starting point from the other side, having circumnavigated the cosmos. The universe is finite but unbounded, like the surface of the Earth, and there is no edge to find. Or suppose the universe is finite but open, a bubble embedded in something else, the inflating bulk of eternal inflation perhaps, or the void of absolute nothingness. What happens when you reach the boundary? This is the hardest scenario to imagine, because our intuitions about boundaries fail at cosmic scales. Would you hit a wall? Would you dissolve? Would you cross into a region with different physical laws, different dimensions, different rules of existence? Would you simply cease, your atoms unable to persist in the non-space beyond? These questions do not have answers, at least not yet. The physics we have does not describe what happens at the boundary of existence, because our theories are formulated within existence, assuming a space-time that already exists and obeying rules that already apply. The edge of the universe, if there is one, might be the edge of our physics, the place where our equations stop working and something else, something we cannot describe or predict, takes over. You drift in your imaginary ship, approaching the unapproachable, reaching for the unreachable. The journey is the point, perhaps, more than any destination. The questions are the point, more than any answers. You're pushing against the limits of the conceivable, and the limits are pushing back, not with walls but with paradoxes, not with boundaries but with mysteries. The edge of the universe is not a place you can go. It is a place you can only think about, imagine, wonder at. And in that wondering, you touch something genuine, something that connects you to every human who has ever looked up at the night sky and asked what lies beyond. The journey ends where it began, with a question. What is out there? Does it end? What happens at the edge? You do not know. Nobody knows. And that is okay. The question is enough for now to carry you into sleep. You're arriving now at a place of rest, a gentle plateau after the long climb through paradoxes and infinities and edges that may or may not exist. The question you started with, can the universe be infinite and still have an edge, has unfolded into something larger and stranger and more beautiful than you might have expected. And the answer, if there is one, is both yes and no, depending on what you mean by universe, what you mean by infinite, and what you mean by edge. The universe might be truly infinite, stretching on forever in every direction, galaxies without end, voids without end, the cosmic web repeating to infinity. In this case, there is no physical edge, no wall, no boundary where space terminates. But there are still horizons. The particle horizon, the event horizon, the limits of observation and causal contact that define what you can know and interact with. These horizons are edges of a kind, personal edges, epistemological edges, boundaries between the accessible and the inaccessible. Or the universe might be finite but unbounded, closed in on itself through curvature or topology, a hypersphere or a torus or some other shape that has a definite size but no edge. You could travel forever in such a universe without hitting a wall, but you would eventually return to where you started. The universe would contain a finite amount of space, a finite number of galaxies, but no terminus, no boundary, no outside. Or the universe might be something stranger still, embedded in a larger structure, a multiverse, an inflating bulk, a quantum superposition of possibilities that redefines what we mean by edge and existence. The edge of our universe might be a transition to something else, not nothing, not absence, but a different kind of being, a different set of rules, a different chapter of a larger story. Historians still argue about all of this, physicists argue, philosophers argue. The question is not settled, and it may never be, but the arguing is not futile. Each argument refines our understanding, sharpens our concepts, reveals new possibilities and new puzzles. The edge of the universe is also the edge of human knowledge, and pushing against it is what science does. Here is a final quirky fact to carry with you into sleep. The word universe comes from the Latin universus, meaning turned into one. The universe is everything turned into a single whole, a unity of all that exists. To ask about the edge of the universe is to ask about the edge of unity, the place where oneness ends and multiplicity, or nothing, begins. It is a question about the nature of wholeness itself, and it has no easy answer. You have travelled far tonight, through ancient cosmologies and medieval disputes, through Newton's infinite stage and Einstein's curved spacetime, through horizons and topologies and quantum fuzziness, and dark energy's relentless push. You have met the multiverse and confronted infinity and imagined impossible journeys to unreachable destinations. And now you're here, at the end of the journey, which is also the beginning, because the questions never really end. The universe is around you now, in the darkness of your room, in the atoms of your body, in the photons that have travelled billions of years to reach your eyes when you look at the stars. You're part of the universe asking about itself, a fragment of the cosmos wondering about the whole. This is strange and wonderful and deeply moving if you let yourself feel it. And so you settle now, letting all the questions drift away like clouds across a night sky, like galaxies receding into the dark. You do not need to hold on to anything. The universe will still be there in the morning, still vast, still mysterious, still beautiful. The edge, if it exists, will still be impossibly far away, and the horizons will still be gently expanding, revealing more of the cosmos to anyone patient enough to wait and wonder. Your breath slows, deepens, becomes soft and steady like the hum of distant stars. Your body relaxes into whatever surface supports you, trusting it to hold you through the night. The questions that felt so urgent are quieting now, not answered but accepted, allowed to be questions without demanding resolution. The universe is big enough to contain all your uncertainty, all your curiosity, all your sleepy wonder. You do not have to figure it out tonight. You do not have to reach the edge or understand infinity or resolve the paradoxes that have puzzled thinkers for millennia. You can simply be here, now, a small warm presence in an unimaginably vast and possibly infinite cosmos, held by gravity, warmed by starlight, breathing the atoms that were forged in ancient stellar cores. The night deepens around you like a gentle hand. The edge of the universe fades from thought, replaced by the soft edges of sleep, the blurring of consciousness, the drift into dreams. Whatever lies out there in the cosmic dark, whatever boundaries or horizons or endless expanses, they will wait for you, patient and eternal. For now, there is only this moment, this breath, this quiet, this peace. Let the universe hold you as you slip away. Let the questions rest. Let the infinite recede into silence. Sweet dreams.